Sì, non è calda sicuramente.
So the second lecture today is from Dr. Minisci, and Dr. Minisci, you received emails from him, and he is actually the coordinator of all the training activities within Stardust. So he will follow closely all the training that you are going to receive during the next 3 years. So he's also the person you can complain with if you don't receive enough training. And the lecture will be about a very important topic on this network, which is the re-entry of asteroids or space debris. Of course, we don't want to have an impact with an asteroid, but if that happens, of course, the first thing that the asteroid encounters is the atmosphere. And for space debris, we know that some solutions involve the re-entry of a piece of debris.
Thanks, Max. Well, actually, more than the re-entry of the space debris and asteroids, it is an overview of peculiarities of the entry flows and techniques for numerical solutions. Actually, a part of the project in Stardust, there will be a research assistant, a postdoc research assistant, who will actually use high-fidelity modeling for the simulation of flow for debris and asteroids. But the vast majority of the work has been done in the past and now, not for asteroids or space debris, but for space planes. And actually, the vast majority of the modeling was done in the 80s and the 90s, when the space planes activities were at the top. And now they are restarting, actually. The lecture will be an overview. Well, the entire argument is, well, from my point of view, is actually extremely complex due to the numerical techniques involved, due to the peculiarities of the flow that will be encountered, will be considered. So I'll try to make this overview as smooth and relaxing as possible without almost any equation. So entry flows, what are the entry flows? Well, basically, we will see that we will speak about hypersonic flows, and we will characterize the term hypersonic. And then we will also speak of rarefied flows, which are both. So I put there, well, vehicle or object, because I want to generalize the argument. I want to use these techniques also for generic object, but actually all the well, 99% or almost 100% of the papers and the books that you find talk about space vehicles. But actually there is, apart from the high speed of entry asteroids, the vast majority of the technique can be used for the simulation also of asteroids and space debris. So the first thing that we have to understand is that the flow field around entry object is evolving during the trajectory, evolving from due to the different regimes of velocities. We have large, of course, velocity entries, which could be up to 30 or 40 kilometers per second for asteroids, or even bigger. And there is also a change in pressure and density through the from the start of the trajectory, atmospheric trajectory, to the last part of the trajectory. It could be the ground, could be some place at some altitude. So we will have that the flow in terms of, let's say, just in terms of characteristics related to the velocity mainly, will pass from hypersonic to supersonic and subsonic. We will speak about hypersonic flow because, well, supersonic and subsonic are almost, well, there is nothing complex regarding those two regimes. I put there not always, because it is not for sure, it is not assured that the object will arrive at supersonic or subsonic regimes. It could disappear, could explode, could break. Another thing that is peculiar to the entry flows is the fact that due to the change of characteristics of the atmosphere, we will actually have different regimes. We will start from the upper part of the atmosphere where we have free molecular flow. Then we go through a part which is called the transition regime. So it is still molecular but with higher density. Then we have the continuum part. And inside the continuum part, when the flow can be considered a continuum, we can have the true continuum flow when the density is, well, high, or actually not the density. We will see that a parameter which is really important is the Knudsen number. But we also have well, actually there are no crisp boundaries between this part of the atmosphere of the flow. So transition regime and continuum flow with slip effects are some buffer boundaries. Just in the continuum flow, what we could use, the difference between the transition regime and the continuum flow with slip effect is that in the second one, we could still use the approaches for to simulate the flow used for the continuum flow with some peculiar boundary conditions at the wall of the object, where actually there is no slip condition. So actually what is done is that instead of having the flow the same velocity of the wall of the object, there is a different velocity, and there is also a jump, a crisp jump between the temperature of the wall and the temperature of the flow. In order to simulate the flow at the molecular regime, we cannot use the same techniques for the continuum regime. We have to solve the Boltzmann equations, and this is done by direct numerical simulation, and could be molecular dynamic, could be direct simulation Monte Carlo method that I will describe later. Let's start with the characterization of the hypersonic flow. the difficulties to simulate the hypersonic flow start since the very beginning. There are difficulties to say when an hypersonic flow is hypersonic. When you have to say if it is supersonic or subsonic, it is easy. You have the Mach number, and if the flow has a Mach number which is higher than 1, you have a supersonic flow, and if the flow has a Mach number lower than 1, it is subsonic. It is not the same with the hypersonic. Hypersonic flows basically, well, we could use what is called what Anderson calls the rule of thumbs, which says that it is hypersonic if the Mach number is higher than 5, but it does not give us actually an idea if we are in hypersonic regime. Actually, hypersonic flow, we are in hypersonic flow when certain phenomena appear in the flow. And actually there are, due to the density, due to the characteristics of the flow at the infinity, and due to the shape of the object, some phenomena could appear at 3, 4 Mach, other could appear at 6, 7, 8 Mach. So 5 is just a rule to simplify things, but there is no crisp rule as to divide subsonic and supersonic, but there is what I call a fuzzy threshold. So there is a buffer zone where below 3 you are for sure in just supersonic, and above 8, 7 you are for sure in hypersonic. So there are few phenomena that you have to recognize to say that we are in the hypersonic. Well, as you may know, when a flow is supersonic, so there is an object is flying a supersonic regime, there is a shock wave. This shock wave actually is closer to the body if the velocity is very high. That means that what is called the shock layer, which is the layer between the shock and the body, is very thin at hypersonic speed. And actually what we can have is that there is an interaction, there could be an interaction between the boundary layer of the subsonic flow after the shock with the shock itself, which is one of the things that should be modeled and correctly modeled to characterize. Another thing that is peculiar of the hypersonic flows is the fact that, for example, in the case of a blunt body, okay, in the previous case we had a very sharp body, sharp nose. Here we have a blunt body, so round with a finite radius at the nose. What happens is that actually the flow passing through the shock wave increases the entropy, but the increase of entropy due to the fact that the shock wave is curved around the blunt nose is different when you move from the axial of the body toward the external direction. So that means that there is actually a gradient of entropy, and it is the creation of this entropy layer. So this gradient of entropy is actually flow down through the shock layer, and the boundary layer of the subsonic flow grows inside, and there is an interaction between the entropy layer and the boundary layer of the flow. So due to the high speed and due to the fact that there is, the fluid is viscous, there is high dissipation. So transformation of the kinetic energy is into thermal energy. that means that actually what we have is very high temperature in the boundary layer, and that actually influences the growth of the boundary layer. And what happened is that due to this different temperature, high temperature, the boundary layer actually is much higher than what can happen for subsonic flows with the same boundary condition, same boundary layer. So actually what happens is that having a boundary layer which is much higher than what should be means that the flow actually sees a different shape. It is like having a fatter and a blunter object, so a different shape. Then, of course, there are problems and effects due to the fact that there is high temperature. High temperature that are due to the viscous effect that we saw before, and this is related to the chemical characteristics and chemical composition of the air. Due to the fact the air, the air, because we are moving in the air. What we have is that we cannot consider anymore the ratio of specific heats as a constant, but it becomes a function of the temperature. And what happens is though also that there are, from a certain temperature onward, there are dissociation and also ionization, depending on the temperatures which are involved. This is what happens in the viscous layer, but we also have high temperatures behind the shock wave. And here what we can see is that after the temperature, after the shock, in the shock layer, but after the shock wave, the temperature could be extremely high, and depending on how we model the fluid, we can have different temperatures. In this case, for example, this is an example. If we consider that the gas is a perfect gas, we have a very conservative value, but too high actually. That means that for the same velocity, we have a difference in temperatures which is several thousand kelvins. Okay. Something more realistic is if we consider the gas not perfect, but in thermal equilibrium, thermal equilibrium. So what we have is that a less conservative value, and which is closer actually to the values that are have been measured on the space on vehicles. Well, especially due to the fact that there is that change, apparent change in the shape of the vehicle, there are also changes in the aerodynamic characteristics of the vehicle. So lift, drag, and momentum on the vehicle are different. And but one thing which is the most important in hypersonic flow is the high heat transfer rates to the surface, which is one of the limiting factors for the design of space vehicles, and it is one of the things that should be mostly considered for any entering object. So we can have two different kinds of heating. We have convective heating from the flow, which is from the flow in the boundary layer, which is attached to the wall, and we have especially after the shock wave and especially at very high speed, we have radiative heating. And depending on the characteristics of the atmosphere, and depending on the characteristics of the, and depending on the speed, well, this, you can have different portion of convective heating and radiative heating. For example, in the Apollo re-entry, radiative heating was just 30% of the total heating. But for the, for example, in the case of a space probe entering in Jupiter, we only have basically radiative heating and not convective one. Now, let's start discussing about numerical approach for this and for continuum, which are different from numerical approaches in the rarefied regime or rarefied part of the atmosphere. Numerical CFD technique actually can be used, but something should be added to take into account the fact that we are operating with hypersonic flows, and mostly because related to the hypersonic flows we have these high temperature effects. So what happens basically is that we should add to the normal equations which are used for subsonic and supersonic CFD additional equations which should take into account chemical and thermal non-equilibrium states. It is important to recognize if we are in, for example, in chemical equilibrium or not. In the field, it is used as the Kamm-Kohler number, which is a dimensional number measuring the level of non-equilibrium. So, and with this number going to the extreme, to the infinity, or to the or to zero, we can have extreme conditions of the flow, where we are in total equilibrium, or the flow is totally frozen. This is usually why we want to. The real flow is in non-equilibrium. But if we want to have boundaries or of at cheaper computational cost, sorry, it is extremely is cheaper and much more simple to consider when we are in equilibrium or when the flow is frozen. Then you have boundaries for example, the heating flow, for the heating rate. For example, here, then I'll go back again. You can see basically that on the left, you can have an idea of what is the level of convective heating. And you see that basically, if it is frozen or if it is in equilibrium, you have basically in frozen, what we can actually easily obtain are solutions here and here, more easily obtained. And then that could give you, you or to designer, the bounds for example, the convective heating, saying that the convective heating should be between these values, even if you don't have the precise value. Another thing that should be taken into consideration when we try to simulate hypersonic flows is the fact that when there is an excitation, when there is transfer of energy to the vibrational state of the vibrational states of the gas, actually there is the possibility that brings to the dissociation of the molecules which are considered. And so this is another effect that should be taken into account when we model. And in order to give boundary conditions at the wall, another thing which is not easy to model is the catalytic efficiency of the wall. So how the wall and the material of the wall is affecting the reactions in the chemical reactions in the flow. And again, in this case, simplified solution can be obtained, or in a cheaper way, if you consider a fully catalytic way or totally non-catalytic wall, and that gives you again some bounds. Okay, so basically, what are easy to obtain are points here, here, and here, but the reality is inside. So if you can obtain, and we can actually obtain more easily those 3 points, we can bound the problem. That is the idea. Another thing that should be taken into account is the modeling of the thermal radiation, which is actually one of the main problems, main challenges at the moment. So which is the approach? I don't give you here the equations, but it's just the general approach is to, if we have a general viscous, turbulent, and flow in chemical non-equilibrium, what we have to solve is a system described by these standard Navier-Stokes equations, plus, of course, Navier-Stokes equations with, in this case, since I consider additional equations for turbulence modeling, I'm talking about Reynolds averaged Navier-Stokes equations. And to take into account the chemical non-equilibrium, we have to consider continuity equations for the species which are present in the gas, in the flow that we are considering. If we are also in non-thermal thermal non-equilibrium, additional equations should be taken in, should be considered for the energy conservation, describing the energy conservation of vibrational excited molecules, and the energy equations for the electron modes. Then this is the complete case. Then if you have subflow, what it calls subflow or simplified flow, for example, if the gas is laminar, you don't consider the turbulence models. Or if the gas is in equilibrium, you don't consider the non-equilibrium equations. To obtain the solutions of the problem, what you have to do is use the normal techniques, almost normal techniques used for computational fluid dynamic approach. So the discretization of the domain and of the equations. And this is mainly due now using the finite volume approach. And then you have to set boundary conditions for example, on the wall, boundary conditions at the inlet, depending on how you design your domain. One thing which is very important is of course, techniques which are used to solve the system are really important, but what is a major challenge is to obtain a fine discretization. Fine discretization means that you have to have a fine grid, a fine mesh, where it is important to catch important properties, and especially to catch the shock wave. Well, this is basically some sort of history. In terms of numerical simulations, the first major achievement was obtained in the 60s when people solved numerically this blunt body problem, which was, it is an envisaged problem that was impossible to solve at that time, because people could not actually understand how to solve the flow behind the shock, where you have, for example, in this case, a region where the flow is subsonic and region where the flow is supersonic. The equations that describe these two different regimes are different, and there was no fine numerical solution for that. Then people understood, for example, that steady solutions could be obtained as asymptotic solution for transient simulation. And in that case, everything is changed. The equations have only one nature, which is the hyperbolic nature, and so it can be solved much easily. After that, people, well, major achievements in terms of modeling were obtained in the 80s and 90s, as I said, because there was this big push in terms of space exploration and space plane design. And after 20-25 years, actually, we still use the same, more or less the same models. There are still problems to predict the heating in the stagnation point just behind the shock wave. Well, what had to be changed? Well, basically, some of the techniques, some of the codes are basically the same, but due to the fact that we have now different computer architectures, faster, all the codes have been rewritten to be used on this. On these things. And that means that also what happened also was that some schemes which were not affordable at the time with fast computer became affordable. So, other things, at the moment we still have problems for grid generation. The problem for grid generation is not actually is mainly due to the fact that we increased a lot the complexity of the cases that we want to treat. Okay, 20 years, 30 years ago, it was well, the major challenge was to solve a part of a blunt cone. Now the aim of industries and research centers is to solve the flow around entire vehicles with meshes which can arrive easily to hundreds of millions points, and with geometries and shapes which are really, really complex to make. So in that case, you can use unstructured meshes instead of structured ones, because unstructured meshes are easier to build, but they pose also some problems in numerical terms. So fluxes of quantities should pass, well, cannot really compute easily fluxes in unstructured meshes. Easily, precisely, let's say. So at the moment, what is the state of the art is, well, schemes. We have to use schemes which especially improve or allow us to capture the shock. There was also application to the hypersonic simulations, to the hypersonic simulation of multi-grid. And of course, what is really important for hypersonic flow is the local preconditioning, which is a technique that is used when you have in the same computation points where the velocity is very small and the points where it is very, very high, which is actually this case. Validation. For validation, one of the things that we have to do when we operate with numerical methods is validate the results against experimental results. For normal cases, subsonic cases, supersonic cases, that is not so difficult, but for hypersonic things, for hypersonic flows, it is very, very difficult. There are few wind tunnels that can guarantee Mach numbers up to 30, well, you cannot actually simulate the real conditions that in those tunnels, and you cannot simulate the hypersonic flow for more than few milliseconds. Can increase actually the testing capabilities using what are called the plasma tunnels, which actually can have much higher testing time. They can reach also temperatures which are close to the ones that that the vehicle or the object experience. They are really expensive. For example, in this case, there is in the Scirocco, which is in Italy. They have an entire power plant dedicated for this, and each run is several thousands euro. Another approach to validate is flying tests, but the flying tests are much more expensive actually, and also time expensive, and the repeatability is not always possible, and that is another case from work in Italy. Rarified flows. Actually, the number which is used, the dimensional number, is this Knudsen number. The Knudsen number gives us the idea of if the flow is and how much rarified. It is the ratio between the molecular mean free path and the characteristic length of the object. That means that depending on the dimension of the object, you can have a factor rarified flow even if you are flying at the same speed or in the same conditions of the atmosphere, same density. So the SMC methods for if we are in rarified flow, and especially if we are in the transition regime here, we have to solve the Boltzmann equation, which is not easy to solve analytically, so direct numerical simulations are used. There are two kinds of the direct numerical simulations that can be used. One is the molecular dynamic that simulates each molecule, but it is very expensive and used only for free molecular flow. And the other one is direct simulation Monte Carlo, which actually simulates a bunch of molecules, okay? A group of molecules. This is just a small advertisement of what we have here and what we will use for this project, for Stardust. This is, we will use the open and open source, open form CFD code, where the SMC module has been built inside, which has been tested and validated, and it is actually apparently extremely easy to use with a good measure, and the idea is to use that for numerical simulations of complex shapes, for example, for asteroids and space debris. Well, just to give you a number, the simulation of this, which is the Skylon, maybe you know this, the Skylon vehicle. Well, the DSMC simulation of this took almost a week on 64 cores. For the simulation, for the validation of the code, what has been done actually is to use test cases and compare the results with existing and already validated codes, which is the Monaco code there. And these are references. Well, I hope this concludes the lecture. I hope it was not too boring. Yeah, we hope to use these numerical tools for the project because there is nothing, almost nothing on high fidelity simulations for empty objects which are not space planes. Thanks.
I heard you made a reference to unstructured meshes.
Yeah.
How are they defined? I mean, unstructured means you make just one mesh for the whole vehicle, or?
Yeah, well, the definition is between structured and unstructured is that probably I should have included that. A structured mesh means that it is a regular mesh where you have that, and it is basically a regular grid where each point there is easy relation between all the points. So when you consider a point, you already know which are all the other points around. Okay, and that doesn't change. Unstructured mesh is a mesh which, for example, is a triangular mesh, which is not a regular grid, and basically you do not know a priori which is the node, the neighboring node, and so every time that you have a mesh, a node mesh, you have to store also which are the nodes which are connected. That is, well, unstructured meshes are used because there are methods that can build them on easily on any kind of complex shape. For unstructured meshes, you cannot have one single mesh. You have what is called the multi-block approach, and especially if there is a very complex shape, you cannot have sometimes total connection between the blocks, and so you have, for example, different number of nodes from one block to the other. But the fact is that structured meshes usually give better results. So there is always this trade-off. It is extremely difficult to build a structured mesh on a complex shape could also take weeks or months to build. Okay, an unstructured one could be a matter of days, and it is almost automatic. It's just computer time. While in the other case, it is human time.
What about you told that most of the simulations published in literature, most of the literature is on reactor space vehicles, and what about breakup simulations?
Well, the vast majority of breakup simulations are done actually in using semi-empirical computation, not high-fidelity models. So what people at the moment do is to simulate the trajectory, simulate the breakup, but associating the breakup with some particular conditions which are expected. What we want to do is exploit the computational resources that we have now, which were not available 10 years ago, for example, and see if those things, well, can be simulated and if they give different results.
I know very little about this subject, so this may be a silly question, but you showed a slide where there was a regime where chemical reactions were catalyzed and another regime where chemical reactions were not. And you said that it depends on the surface. Does it depend on the material the surface is made of, or the roughness of the surface?
Mainly the material. Is the material, yes. The catalytic effect of the are related to the material which is considered. The problem is that, for example, for space vehicles, if you have if you have the surface is covered by thermal protection systems, and many times this thermal protection system has not been characterized well, so you never know which are the real properties of that material and how those properties change with the temperature, because what happens is that these problems also change, these characteristics also change with the temperature. So it is a very interconnected problem, and it is very difficult to understand. So there is a huge amount of uncertainty. It is almost impossible to say that, to fix a particular value and to expect that the real flow will behave in that way, and the real material.
So when I understood correctly, you can simulate the flow around structures with this code, but can you also simulate, for example, an explosion of an asteroid, so a blast wave or something like that?
Yeah, well, the idea, I didn't mention, but the one thing that should be done also, even if you do not consider the explosion, or you do not consider the change of the shape, a proper fluid dynamic simulation, especially in hypersonic conditions, should be coupled with the structure. Okay. And that is particularly true when you expect that the object ablates, or when you expect that the object breaks, or, well, breaks and explodes, or that kind of thing. So the idea is to couple, things should be coupled, structural and fluid flow simulations, which is not easy.
Okay, so my question is, when an object re-enters, is going to first encounter a free molecular flow in position region, etc., etc. So basically, the environment changes, the environment experienced by the object changes over time as it goes along. How do you deal with these simulations? Because this is not a steady state solution, just a number of solutions that follow in the transition period.
Yeah, well, actually, the ideal thing, which is, I think, not affordable now, is to consider and something that we do for design is to consider the coupling of the fluid dynamic simulations and trajectory simulations. Ideally, and probably will be could be done in the future, you can couple those things and simulate the unsteady flow during the trajectory. At the moment, the only thing that you can do is to hypothesize the sum of the points of the trajectory, and then analyze those points with different tools depending on the density, or depending on the Knudsen number, and depending on the speed and the expected chemical properties of the flow. Which is what is actually done for design of the vehicles. When you design a vehicle, you tend to consider few points during the trajectory, or what should be the trajectory, and then analyze those points.
Okay, so just find the solutions for a particular point, and then sort of try and interpolate between those and see.
Yes, that basically.
But maybe if I can add something, when we design a re-entry trajectory, we have this sort of contour points in which we compute the fluid dynamic solution, and then we update the trajectory based on the outcome of the calculation of the fluid dynamics. Okay. And it's a very lengthy process, because and actually we now can do it optimizing the control of the surfaces of the vehicle to pinpoint a location on the ground. So we solve an optimal control problem coupled with a numerical simulation.
How big a supercomputer do you have?
Well, we use multi-fidelity techniques, so the vast majority of computation is done with low-fidelity models, and then high-fidelity models are used just to correct the predictions. Otherwise,
One question. The term explosion, when the people refer to explosion in a reactor, is it appropriate or
well, no. I use the, well, for me, what I use is two things can appear, ablation and breakup. But, well, depending on the speed of the phenomenon, could be an explosion.
it's a sudden breakup that
Yeah.
people
Think is,
correctly refer
yeah,
to?
exactly.
Okay, we can move on to the next speaker and the last lecture of the morning.